In this video, I'll be demonstrating a simple double sideband transceiver for 40 meters using only discrete components. It's really simple. No surface mount, no ICs, and all discrete transistors. Just 8 of them all up. Some stages work on both transmit and receive, simplifying the circuitry further. We'll have a look inside, I'll run you through the circuit, and with any luck we'll get on air to see how it works in practice. First of all though, we need an antenna. Now with a lot of videos, people ask me what sort of antenna I'm using. This time it's the usual end-fed half-wave antenna. If you want a description, you'll find it in several other previous videos. Have a look particularly at minimum QRP part 2. Having a look inside, just behind the tuning capacitor is the ceramic resonator oscillator and its buffer. Just up here, mounted paddy board style, is the balance modulator. You can see the 2-hole ferrite choke used for its output coil. Here's the microphone socket, and behind it is the audio amplifier for the transmitter. That drives the balance modulator in transmit mode. Next we have a transmit RF amplifier. That's low level. That amplifies the double sideband straight from the balance modulator. Next we have the driver stage, which is a BD139. I'm using similar ferrites to those in the balance modulator. Finally we have the final amplifier, another BD139 on its own heatsink. Behind that is the transmit receive relay, and behind that again is the Pi network. That's a low pass filter mounted straight behind the antenna socket. On the other side there's not much, just a 2 transistor direct coupled audio amplifier. Surprisingly, that can drive low impedance phones, but the volume is a little bit too low, except if you're in a quiet room. Therefore, for portable use, I'd suggest adding another stage. Or you could use an LM386. There's enough board space left for that here. Now we'll draw a circuit of the 40 meter double sideband transceiver. Start off with the oscillator. I'm using a 7.2 MHz ceramic resonator, and that's in series with a transistor radio tuning capacitor, about 10 to 160 picofarad. Now if you don't have a ceramic resonator for 7.2 meg, you can just use a crystal, but your pulling range will be less. To increase the pulling range of a VXO, ideally you have 2 or more crystals in parallel and a series coil. The values are fairly critical, but you should be able to get quite a good range, maybe 30 or 40 kHz shift for 40 meters. As for the crystals you could use, 7.159 MHz is a common crystal frequency, also 7.122 is another. The oscillator transistor, just a standard C548. Now that's your 12 volt rail to the oscillator. Buffer stage, very simple. Now the balance modulator. This design I first saw in VK QRP's SSB transceiver, and it works very well. 200 ohm balance pot. Diodes, a bit like a bridge rectifier. They're 4 1N 4148s. Now you've got a balanced pot, 200 ohm, but to get really good balance, it helps if you've got a trimmer capacitor. This other capacitor can be fixed. It's 22 picofarads, this one's 4 to 40. And you get really good carrier suppression. The diodes, by the way, 1N 4148s. Now with a lot of balanced modulators, you need bifilar coils. Well, this one's a bit simple. 4 turns to 10 turns on just a ferrite toroid. Now the balanced modulator also performs as the receiver product detector. But for now, we'll base this on a transmitter, so we actually need to apply some audio. The audio comes in just at the top of the 10 nanofarad capacitor. If we're using an electret mic, we do need a bit of amplification. That's where this circuit here can help. .100 nanofarad. You can go higher values, but you might have too much low frequency response. It's good to roll off both the lows and the highs. We are talking communications quality only. Again, ubiquitous BC548. You could use a 2N2222. It's 220 ohm there. 68 microfarad. That's an electrolytic. That's 100k. Now that's plus 12 volts, but on transmit only. Audio comes out via 1 microfarad, and it goes into the balanced modulator. Now this point here, the input of the balanced modulator, is also the audio output from the receiver. We'll talk about that a bit later on. Okay, so what do we have here? We have a local oscillator, in this case at 7 megahertz, feeding a carrier through a buffer into a balanced modulator, 4 diodes there, and that is mixed with the incoming audio, which is amplified from the electret microphone, and we have here a low-level double sideband signal. It's too low level to be of much use, so we need to amplify it. running out of space here. 100 nanofarad, 1K, 2.2K. Here we're using a 2N2222 NPN transistor. It's 100 ohm, 10 ohm, 100 nanofarad. It's grounded. Now, bifilar toroid, about 10 turns on a ferrite toroid. The tap is connected to the power connection via a 100 ohm resistor. It's at the top of the page, you might not easily see it. Anyway, that's plus 12 volts, but only on transmit. Now that same connection is also used to power the transmit microphone amplifier. 100 nanofarad to earth from the power connection. The output of the toroid free end, that goes to the following stage. Now, to bifilar wind this coil, you just take enamelled copper wire, like from an old transformer, something like that, and you twist it together. What you can do, you can get a hand drill. You just put your hand drill between your knees, you just put the two ends of the wire into the chuck of the drill, then you get some pliers, you hold the other end and you crank the drill. That's one way of doing it, or if you've got a vice workshop, then that's probably a better way as well. The idea is you have twists about every 4 or 5 millimeters. It needs to be fairly even, but you don't want to tighten it up too much, otherwise the wire breaks, and you don't want it too loose either. As for the length of wire, well, you can do some calculations. If the toroid's about that big in diameter, one turn is probably about 2 centimeters of wire. So you start off with, say, 30 centimeters of enamelled copper wire, and cut off the ends as desired later on. Some take the view that if your transceiver requires more than a page to draw the circuit, it's too complicated. So I'll try and cram this all on the one page. I'll finish off the rest of the transmitter, try and cram things in. From the first 2N2222 transmit power amplifier stage, we need another amplifier stage. So the RF comes via 100 nanofarad capacitor, 470 ohm to earth, 2.2K, another transistor. This one is a BD139, which is quite a good RF power transistor, but here I'm using it at a much lower power level. 22 ohm, that's in parallel with 4.7 ohm, which is in series with another 100 nanofarad. You'll use lots and lots of 100 nanofarad capacitors for RF circuits, so buy a lot of them. If you can get 100 cheaply, then you will definitely use them all. Another bifilar round toroid, again the same deal as before, just a ferrite. I use, you can either use those round FT 5043 toroids or those TV balun formers. They are actually look like little pairs of binoculars. They're about that long, and you just wind the turns, you just loop them through, and they work quite well. And you often see a lot of old TVs around, or old TV antennas in junk shops, garage sales, or even on the streets. You just have a look at the baluns. They're often used with indoor antennas. They match the 300 ohm to the 75 ohm. Anyway, crack one of those open and you'll often get a balun former. So they are really good sources. Anyway, we've got power applied to the junction of the windings. again another 100 nanofarad. The RF comes out via yet another 100 nanofarad, 330 ohm to ground, 6.8. Okay. Another BD139. This is our final transistor. It does need to be on a fairly good heatsink. This time the emitter is earthed. Collector, well, this time I'm using just a 6-hole ferrite bead. And a couple of capacitors to earth. One is 100 nanofarad. Another we'll use an electrolyte, something like an electrolytic, something like 220 microfarad. We don't need any series resistor to the supply because the full current is needed, it being the RF power stage. So that is plus 12 volts on transmit only. So that's connected to the microphone amplifier and the earlier amplifier stage. 100 nanofarad, this is the RF output. Now if you wanted to be really quick and dirty, you just use a double pole, double throw switch for the transmit receive switching. But in this case, we'll use a relay for the push to talk. So you can connect that to the push to talk button on your microphone. One set of contacts is for the power, switching the 12 volts. You've got some stages which are on all the time. That's the local oscillator at 7 meg and its buffer. Other stages are only on receive. That's the receive audio stages that we'll talk about later. And still other stages are only powered up on transmit. That's the microphone amplifier and the transmit power amplifier chain. So use one set of contacts in the relay to switch that, and the other set is used to switch the antenna connections. You could have a low pass filter immediately following the power amplifier, but I'm going to have it in both the receive and the transmit part of the circuit. So it's in the antenna line. So we take the middle connection of the relay, the bit that switches between one and the other, which is the antenna line, and we'll put in a pi network. 440 picofarad here. I'm using two lots of 220 in parallel. 1 microhenry RF choke, wound on a toroid. 820. Another 820. You can get away with ceramic capacitors, but if you've got polystyrene, they are better because there's lower loss. Note with a pi network, in this case it's a symmetrical circuit. 440 picofarad, 820, 820, and again 2 lots of 220. And that goes straight to your antenna socket. So we now have a transmitter, double sideband, 40 meters, and it puts out around 2 watts output. All we need is to make it a transceiver. It's simpler than you think. Because a double sideband transceiver and a direct conversion receivers are almost direct opposites. They use a lot of the same components, and you can reuse some of the stages. In this case, I'm reusing the local oscillator, its buffer, and its balance modulator. That's also a product detector on receive. So all we need is an audio amplifier. Again, use 2 lots of BC 548s. .7 microfarad. Now that goes to the balance modulator, the audio tap on the balance modulator. It's also used on transmit, where audio from the mic amplifier is injected, but this time we're using it in reverse. So 4.7 microfarad coupling capacitor, okay. Might run out of space here, and the collector is 2.2k. This junction is a capacitor, make that 47 microfarad. Another resistor, 100 ohm only. Another capacitor, 220 microfarad. Now, from the collector of the first audio amplifier transistor, usually you have a coupling capacitor, but in this case we'll go direct coupled, so it goes straight to the base of the second transistor. The free end of the 47 goes around to its emitter. From emitter, 330 ohm, and that's in parallel with 10 microfarad. Two lots of VC 548s. Collector, 2.2k, coupling capacitor, 4.7 microfarad. Now, headphones. A crystal earpiece will work. These sorts of circuits are normally high impedance. However, surprisingly, there's enough gain to drive low impedance phones, especially if you connect the two sides together. You do that, here's your typical stereo plug that goes to your headphones. That's the earth, that's common to both. You don't use that, you instead connect one side to the middle part, the other to the tip, and that connects both phones in series. That doubles the impedance and is a bit more suitable for this sort of amplifier circuit. Now we're applying power here, plus 12 volts, but it's receive only. And that's your complete circuit for your double sideband 40 meter transceiver. Putting out around 2 watts, it's capable of contacts up to about 3,000 kilometers, although those are a bit of a struggle. It's better for more reliable communication up to around 1000k. We'll go through the circuit again. Starting off, we have a ceramic resonator or crystal oscillator. That provides the 7 MHz signal, required for both the transmitter and the direct conversion receiver. A tuning capacitor allows some frequency agility. With a ceramic resonator, you can get a couple of 100 kHz shift. With crystals, it's harder to get a wide shift, but you can get a usable range if you have 2 crystals in parallel and you have a series coil. That value is critical for the best range. If your coil is too high a value, you may get a wider range, but your stability will suffer and the crystal may lose control of the oscillator. The output then goes to a buffer. Again, a simple BC548 transistor stage. The output from the local oscillator goes into the balance modulator, which is also a product detector on receive. I neglected to mention this before, but on receive, The RF from the antenna connection via the Pi network goes into the balance modulator at this point. It's the same point at which RF is taken out of it for transmit. The audio is then taken out of the balance modulator product detector and then fed down here to the 2 transistor receive audio amplifier. A direct coupled circuit often seen in Sprat designs. That then drives your headphones. Or you can connect an amplified speaker for better volume. Getting back to the transmit, the low-level double sideband signal from the balance modulator goes into an amplifier stage using a small signal transistor, a 2N222 in this case. Its collector circuit is broadband using a toroidal former. This is the microphone amplifier stage, a simple audio amplifier. If you are clever with the switching, you could probably also use it in the receiver. But you get to a point where switching becomes so hard that it's easier just to duplicate the components. RF from the transmitter is amplified in a BD139 stage. That goes to a further BD139, which is the RF power amplifier. You could use another transistor like a 2N3053, not quite as powerful as the BD139, but you should still get about 1 watt output. The transmit receive relay, 2 parts are used, one to switch the RF and another part, which I haven't drawn, to switch the DC. Antenna connection goes via a Pi network, switched either to the transmit power amplifier or the receiver front end. That's very simple indeed with this design. Straight into the product detector. The receiver is sensitive enough not to require an RF amplifier. But to improve performance, and in particular rejection of adjacent signals, such as shortwave broadcast stations, you may be better off with it putting in a tuned circuit somehow.
Yeah, I heard you there and I thought I'll put the linear on, I should break through on that little rig, you should be able to hear me. Straight on to you, and I mean I can see Chelsea Beach from here.
Calling me, this is VK Italy Hotel, over. Yeah, g'day Peter, we've met, I've certainly worked with you on Chelsea Beach before, and very good on the homebrew double sideband transceiver. I've got a homebrew sideband transceiver for 20 metres and one for 80 metres, and a homebrew transceiver for 40, but it's an AM transceiver. I do have I've modified a Codan for 40 metres, so that half counts as homebrew there, Peter. But yeah, good signal. I wouldn't have noticed it was double sideband, I'm sure, unless I'd moved the VFO off, but the other one. I've got a little 80 metre double sideband transceiver around here somewhere. It works quite well. It's very low power, but it works quite good on 80 metres. I tried building an amplifier for it, but it was a bit tricky. It works, but not great there, Peter. But I think we met when I used to work at the park ranger down at Wilson's Prom. I think we might have met there once. VK3YE, VK3 Italy Hotel.